All this fight in me, a crown of light on my forehead, where I keep my thoughts discreet.
Polar, and now we're on to cylindrical. Cylindrical. Okay, so cylindrical coordinates, use these when you have a triple integral, okay? So not double anymore, but now triple integral. And when your domain, when your, well, now we'll call it a region. Remember region W. When your W, or region, has what's called axial symmetry. And what this means, the word axial, that just means with reference to an axis. So like the x-axis, the y-axis, or the z-axis. So either if your region is symmetrical with respect to either or any, I guess any one of those three axes, then you can employ cylindrical coordinates. So what this means graphically, let me show you a picture here. Get a straight line going. Okay, there we go. So here's our z, our y, and our x, y, and z. So this might be a bit complicated. Bear with me on the pictures here. Okay, so we have that, and I'll go like this. I'll explain what the picture means and everything. Okay. Or you might be able to see it yourself. Okay, so let's say we have this, like, not really a cube, but it's like a curvy cube in space here. It's floating somewhere. And then, so this is our W, all right? Because now we're integrating over the solid, because we have a triple integral. And what we have is this top thing here, since it's curvy, this is a surface, all right? So on top here, we have some kind of surface. And then on the bottom, we have some kind of surface as well. Okay, so the top surface, this is characterized by z1 of r and theta. Okay, because again, okay, so sorry, backtracking here. Cylindrical means our variables are not going to be x, y, z anymore, and they're not just going to be r and theta, because now we're working in 3 dimensions. So what we're going to have is basically cylindrical is polar coordinates, so r and theta, plus the z. It's basically polar taken to the 3rd dimension. So then you just add the z in. Okay. So this z1 of r and theta, that characterizes this top surface here. And I'll actually make this a 2. All right. I'm just switching notation. It's not that significant. And then the bottom can be z1. I'll just make the lower one z1. Okay. All right. So that's what the top and bottom surfaces are represented by. And then I want to show you something about the other coordinates, the r and the theta. So z, as we just determined, I'll just write it here clearly. It ranges from z1 up to z2. Okay, because it can't go below z1, that's its lower surface right here. And the upper surface, which it can't go above, is z2 of r and theta. That's like the ceiling and this is the floor kind of thing. Okay, in this weird like shaped room. Okay? Alright, so we determined the bounds for z, and now we need to figure out what's the bounds for r and theta. But that's kind of hard. It looks kind of hard on first glance, because you're like, well, this cube is like floating in space, so how am I supposed to make any sense of where it is on the xy plane? So when that happens, what we like to do is, remember projections, when you like shine a light from up here and then this creates a shadow straight down. So let's say the shadow looks something like this. So we have something like that, and it goes out like that. Okay, so this is the shadow that it casts. All right, and this is actually our domain. Remember, this is the domain in the 2D sense. Okay, so what we have is it just goes back to polar coordinates. So here's our well, let's say this continues into some function, right? So basically what we have is the inner function here, which is the part that I'm darkening. This is our R1 of theta, and this is our R2 of theta, the outer one, when you're considering the origin, right? You hit R1 first, and then if you go all the way to the outer edge here, you hit R2 of theta, okay? So picture it, remember, let's say here's our XY plane. Now I'm just putting it flat so you can see better. Let's say this is what we actually have, something like that, and I'm just drawing it here. So like that. So what I just did was label this part R1 of theta, and this one R2 of theta. Okay, so it's this thing, these little curves. And then also we have, we can't forget about theta. So theta goes from, it's the simplest, so it goes from theta 1 up to theta 2, all right? So that's this region here. This is like our domain. So R, again, reviewing, we have it going from R1 of theta to R2 of theta. And then lastly, the most simple is theta going from theta 1, which is a constant, up to theta 2. All right? So basically what we would have here, I'll set up, well, okay, make sure you have take note of these bounds, and we'll be utilizing them in the next slide when I set up the actual triple integral. Okay, so like I said, we're basically using, cylindrical is basically polar plus z, plus z stuff. So polar, again, the relations between rectangular and polar were x equals r cosine theta, y equals r sine theta, and then in this case z is just going to equal z. Yay, how exciting. Okay, so these are the three like translations kind of, and then what we're going to do with the bounds that we found in the last, well, I'll just rewrite them here real quick. So z goes from z1 of r theta, and then z2 goes from goes up to z2 r theta, and then r, same thing, r1 of theta, r2 of theta, and theta itself goes from theta 1 to theta 2. All right, so we're going to set it up kind of like we're doing polar coordinates, but then add in the z at the very last minute kind of thing. So what we have is, let's start from the outside. So we're going to have our theta on the outside, because it's the simplest, right, because it has constant bounds. So I'll write all the way over here, okay? And then we have our r, so from r1 of theta to r2 of theta. And then we have our dr. And remember, we're going to be doing the same thing as polar, so we can't forget the r right here. I always think the r and the dr go together. So r dr and then d theta. And then, like I said, the last thing that we're going to do is add in the z part for cylindrical, right? So then we have our z bounds, which go from z1 of r and theta, and z2 of r and theta, okay? And then we have this dz, all right? And now, what do we do with the middle? Instead of f of x, y, z, which would be in rectangular coordinates, now we're going to plug in the polar ones, just basically all of these. So instead of f of x, y, z, we're going to plug in these little equations for each variable. Okay, so then we'll have r cosine theta, comma r sine theta, comma z. Okay, so that's basically it. This is how you set up cylindrical coordinates. So as you see on the outside, at least looking at the two outside things, these bounds would be the same for polar. This is the same for polar, and then you just add in this middle component here with all of the z stuff, all right? And then you can just ignore that. But okay, so that does it for cylindrical, and now we'll go on to the last category, which are spherical. Okay, so
Lights are low and the circus fades. You were always carried still in all the circles, traces of turn.